Thanks, yeah, and thanks for the invitation. I actually did an REU here as an undergrad, so it was definitely, IPAM was a really special place for me. And really enjoyed the summer opportunity. So I'm going to start with a bit of a promo video. Scientists are not really the target audience for this, but it's got some cool visualizations, so just kind of bear with me, and I'm going to get into some technical details and some blemishes later on, but we're going to start with just some pretty pictures.
Weather has a profound impact on our daily lives. Predicting how it will affect agriculture, energy, aviation, and emergency response is critical. But the atmosphere is chaotic, and forecasting is complex. NVIDIA Earth 2 changes the paradigm. It accelerates the AI revolution in forecasting by offering developers and researchers an open set of tools that lowers the barrier to AI-enabled weather simulation. Building on the impact of models like ForecastNet and CoreDiff, NVIDIA Earth 2 is now a complete portfolio of open models. Introducing Earth 2 Global Data Assimilation, Nowcasting, and Medium Range. To initialize predictions, Earth 2 Global Data Assimilation models turn observations from diverse sources, like balloons, satellites, and stations, into atmospheric states in seconds, a task that previously took hours on high-performance computing clusters. Earth 2 nowcasting models offer severe weather prediction at continental scale from 0 to 6 hours. They represent the first time AI has surpassed the accuracy of physics-based forecasting of storm evolution. Earth 2 medium-range models deliver 15-day global forecasts with accuracy that outperforms other open models on standard benchmarks across more than 70 variables. Earth 2's models span the complete forecasting pipeline. When they're combined, weather can be simulated at speeds previously impossible, minutes instead of hours or days. And because Earth 2 is completely open, not just model weights, but inference tools and training frameworks too, developers can customize and fine-tune simulations to specific needs, using their own data and infrastructure to build sovereign weather and climate predictions with full control. See into the future of weather with NVIDIA Earth 2.
So a bit about my role. A lot of people ask what we're doing at NVIDIA. I think that the video was sort of NVIDIA's take on what we're doing, but my role, I really see it is to help the community build fast and accurate weather models and on our GPUs. And so I think there's a nice alignment between our modeling, because it's really about showing how to use the new advances in accelerated computing, and less about planting flags or being seen to be the best as building the best models. So my personal areas of focus have been on climate emulation, data assimilation, and some of the core algorithm development. Agenda for the talk, there'll be sort of 3 main sections. The first will be going over quickly all the different types of modeling that exist in this landscape. Then we'll talk about how to map those different types of models onto our hardware, and then also some interesting data limitations that we've seen. So you saw the video. To give a little bit more detail on the 3 models we released, the first is Atlas. It's a medium-range weather forecast model, similar to GenCast, and it outperforms GenCast on CRPS as well as RMSE metrics. And so green is good. NVIDIA's green is our kind of our logo, so we tend to use this color bar for things where green is good. And we have a few different versions of the model. This is the one trained with CRPS loss, and so I'm proud to say that this Atlas model seems to be competitive with some of the best forecast models out there. And it's trained only off of open data. I think this was something that I thought was a bit of a hand wave in the promo video, but it seems that not training off of closed data sets is something of value to the community, especially Kat talked about that in her talks. So the next model is this data assimilation model, which goes from raw observations to atmospheric states. You can think of it as an ERA 5 emulator. We're calling it HEALDA. It's on the HealPix grid, which people have mentioned. And this is a really messy field, so these plots are all taken from quote-unquote plot digitization, meaning we looked at the plots in people's papers and extracted the numeric values. But it seems that HEALDA is better than the other AI models out there, but still worse than physics-based data assimilation schemes. So that's kind of our best thrust, and we do a lot of sensitivity tests in this paper, kind of explaining why. And then the third model discussed is this storm scope, which is a nowcasting model. And the blue curve is storm scope, and compared against some basic basic baselines for nowcasting, we can see that, generally speaking, we're outperforming both physics-based model HER as well as extrapolation technique with pi steps. Okay, so that's basically 3 minutes in and trying to end the sales pitch portion of the talk. I think we have a pretty useful set of models that all integrate together, and they're all open and trained off of open data. So please come talk to me if you want to use any of them. But taking a broader perspective at how NVIDIA GPUs can help the Earth system modeling workflow, I thought I would kind of show these cute AI-generated icons of what the Earth system modeling workflow is. So the way it works now is you have theory and data kind of both going into creating interesting simulations. So simulations can be either with physics-based methods or with ML. And then there's the simulation output gets dumped onto a hard disk, and there's usually some post-processing that happens. And then the post-processing happens, and then finally it's disseminated out to the user community. And I think with the traditional workflow, all of these steps take a really long time. And what happens is models really start to improve the more times you iterate through this whole workflow. And I think that's where some of our ML models and some of the accelerated computing can really help us in just speeding up the time it takes to traverse this graph. So when we talk about building the different types of ML modeling, I think we all have in mind what we mean by the term foundation model. And I think foundation model is sort of what a GCM is. Earth system modeling was perhaps one of the first disciplines to have a foundation model, just traditional numerics. And what it is we saw a nice summary of that earlier, was just that it can be used for a few tasks, not just one, that it can bridge different data modalities, which we see with data assimilation systems, that you can do cool what-if experiments and have interactive workflows. And then it's also scalable to all the different resolutions that one tends to care about. And so there's two dominant ways to do this, both in physics modeling and AI modeling. Not really that different. The dominant paradigm is this autoregressive paradigm. So this idea that you can lay down some Markov process and step forward in time to produce a realistic simulation. So the pluses are that's really how the physics work. It's how GCMs work. All the best AI models for weather forecasts are built in this framework, and it's very easy to train. Some disadvantages are that it's more data intensive. To make this a deterministic task, you need to provide the full atmospheric state as an input. And then there's also no really guarantees about what's happening as n goes to infinity. So we've all heard about this like hallucinations idea in LLMs. It's the same thing that we see when a model blows up or the climate drifts. So we're supervising the model at a much finer time scale than it ends up being used on. And it also can be difficult to control. So control of a nonlinear system is quite difficult, despite the fact that data simulations seem to be working pretty well. On the other hand, we have denoising diffusion models. Those are also a time-stepping procedure, but they have a limited number of steps, and they're grounded in theory that sort of tells us that it will produce a realistic-looking answer. So I'll go into what I sort of think is where the thrust of climate modeling in the physics-based context, which is most aligned with kind of accelerated computing, is this move towards extremely high-resolution simulations. And so this is maybe the most well-documented, at least, effort in this regard is the NextGEMS project out of Europe. And they basically pit two climate models against each other, ICON from Max Planck Institute and IFS from the ECMWF. And they sort of developed these through multiple cycles. So each cycle was about a year of development and ended with a hackathon. And they were focusing on two things. One, that the temperature doesn't really go out of range, and they have energy consistency, which ICON struggled a lot with, actually. And then also throughput. And so I'm highlighting here just the throughput in terms that they achieved at 5-kilometer resolution. So they achieved about 100 simulated years per day. And this was sort of the best in the business in physics-based modeling. Years per day, days per day. Simulated, sorry, yeah, days per day. So they achieved about, a third of a year, not 100 years. Yeah, if they did 100 years per day, we wouldn't bother. And the prevailing climate emulators are also autoregressive. So I would say that for the most part, most advances in this discipline, apart from things like graph DOP, have been in this category of emulating the output of existing physics-based systems, be it Era 5 or a climate model. And we see some really nice successes here. We've seen these highlighted before. ACE2 from the Allen my old employer, the Allen Institute for Artificial Intelligence, as well as Camulator from David John Gagne's group. And both of these seem to work quite well. It's kind of remarkable that you can train them on 6 or 12 hours and roll them out for hundreds of years. An important challenge that we've been working on especially is how do we scale these kind of methods to higher resolution? And this requires both potentially a huge investment of resources as well as and in the acquisition of data set. My work has a lot been focused on how do we not use all these GPUs to do this kind of modeling task. So this is just showing an OLR field from an icon output. And some early thrusts we made in this direction were using diffusion models, which have this kind of attractive downscale flow of information, which makes it very easy to scale. So we found in particular that the super resolution task is quite scalable for diffusion models. And so we built a thing called Climate in a Bottle. And the idea is that we can take very large climate simulations and compress them into an ML checkpoint, and then put all of the cost on the inference side. And these are showing fields generated from Climate in a Bottle at 5-kilometer resolution. So it's around 15 million pixels. And it's I think it's like probably, it's in terms of resolution, higher than, it's about 4K. So it's about as high resolution as we see in the ML world. So we have some methods for kind of scaling this. It's actually only trained off of, I think we trained off of 8 GPUs. And we were able to inference this on a desktop in a live demo with 1 GPU. So I think that it's kind of overstated the extent to which you require a really large amount of resources. A lot of that is because we just have them laying around, and so we use them all in the paper, and it turns out you can just oftentimes use far fewer than you'd think.
Can you run it for an arbitrary region, or has to be global?
It can be global. So the global inference, we can run it in an individual subdomain, which will be faster. So it's trained off of individual patches, so you can kind of overlap the patches. It's called multi-diffusion. Not going too much into the details, but I'd be happy to talk about it later. Some other cool things that you can do with this diffusion modeling paradigm that you can't do as easily with autoregression, although you can in some extent, is the left is just like our model versus existing climate simulations. You can see it actually underdoes the response to surface to SSD changes in AMIP configuration. So as a sampler, I would say that this model is not perhaps what you would use if you're interested in the coarsest resolution features of the climate. But what's really good at is adding information to your existing climate model data. So we have this figure that shows all the different ways you can use diffusion models. The first is the upper left is showing some raw Era 5 fields of cloud as well as rain. And you can translate those using a multimodal translation technique. It's called a diffusion bridge to another draining distribution. So we can translate Era 5 to a climate model simulation. You can see that the clouds get a lot stronger because ICON has a lot of clouds. You can also fill in missing data. We didn't use the OLR fields from Era 5 because they have an artifact. They use the seed as lat plus ln in the radiation scheme, so you can see these sort of diagonal stripes in the radiation field, so we didn't use those. But you can fill those back in based off of the observed relationships in the ICON data. So we turn off two data sets. And then you can do the full end-to-end pipeline, which is you take Era 5, translate it to ICON, and then super resolve. And so you can kind of dance between your data islands. Some islands you have paired training data for super resolution with a high resolution model output. Some islands you don't. And so with this kind of method, you can integrate all the resolutions across the data sets that are available. So we have 2 main approaches, autoregression and this diffusion modeling approach. In terms of how do we map these algorithms onto the GPU, that's the focus of the next few slides. So the context here is that Moore's law is ending. The transistor sizes are no longer getting halved. Eventually, we're going to hit a physical limit. And so computing stacks are having to change to accommodate this new physical reality. And the way that they're changing is by becoming massively parallel. So this shows an architecture diagram of Volta, which is actually around 2017. And so one of the most important data center chips that we had a lot of innovations. And so the key features to note here are there's all of these small boxes. These are individual groups of processor called streaming multiprocessors. And then I think the most hard to see part of the plot is this HBM. That's high bandwidth memory. That's where all of the memory sits on the chip. And this memory has to get fed onto the processors. And so that's the most important aspect to note about this, zooming in, is how do we get the large amount of memory that, say, a climate simulation has, it's a huge amount of data that needs to be held on the chip. How do we get that into the processing units? If we zoom into our processing units more, streaming multiprocessor, you'll note that, I think this is a schematic, this is not actual silicon, but you'll note that a huge percent of the streaming multiprocessor is oriented at something called the tensor core. And the tensor core was introduced in Volta generation and has gotten beefier and beefier as time passes. And it basically does reduced precision matrix multiplication. And it only does reduced precision. And so this is kind of an interesting thing, and I'll get more into this in the talk, is this is not really the way a lot of numerical methods for physics-based models look these days. It does look a lot like AI. So essentially, the GPU is becoming more and more of a matrix multiplication machine, and while still supporting bespoke other operations, that's what it's optimized towards. So we can see this in terms of the ratio, as I was talking about the memory versus the compute. These are the most important concepts to keep in mind. Essentially, the bandwidth that you can move data from the memory onto the available compute, and then the amount of data once it's on the compute, how quickly you can process it. So that's this ratio of teraflops to memory bandwidth. And so we can see that for double precision, this is 5, meaning I only need to load, per byte, I need to do 5 operations in order to break even. But we see that as we move towards reduced precision with this half precision, we actually, for every piece of information we load from high bandwidth memory, we need to do something 275 times to make up for that. And so that's the really important division between something that's called memory bound and compute bound. So this, if we look at different algorithms, we can figure out what's called the arithmetic intensity. So that's the ratio of operations to the amount of input and output data required. So if we look at addition, say of 2 matrices that are size n by n, then this ratio is order 1. So we essentially do we load a piece of data, we do 1 operation on it, and then we send it back to main memory. So that's order 1. If we look at matrix magnetic product, also order 1. Now, it's really where you start to do the matrix multiplications, A times B, where you get the n cubed in the numerator there, and you're really starting to actually utilize the tensor core hardware. And so these numbers here are what map onto that ratio that I was showing before. And so if we look across generations, what's been happening is that we look at the flops to byte ratio and compare that with the arithmetic intensity, keep it in your head, the arithmetic intensity of matrix multiplication. We can see that between Ampere generation, when I started at NVIDIA, we were all using Amperes, now we're using Blackwell. Between these 2 generations, something happened, 160 to 295. Anybody want to guess what happened in between Ampere and Hopper? ChatGPT. So ChatGPT happened, and NVIDIA decided, whoa, we need to optimize on this workload. So they made the chip a lot more math heavy. So the takeaways from this kind of overview of the NVIDIA GPU is that there's two basic ways that algorithms can fit on the GPU. They can either be memory bandwidth bound, or they can be bound on the tensor cores, so compute bound. And AI methods tend to be compute bound, and numerical methods tend to be more memory bound. And I think there's some challenges here, some trends that numerics and other methods and climate modeling writ large have to keep up with is a trend towards reduced precision. We're not getting rid of support for normal scientific computing workflows, but to really get the enhanced speedups, following these trends towards reduced precision and more math-heavy operations is important. So if we go back to where I was talking about before, the sort of 3 different paradigms of modeling, basically the modern ML architectures are built off of matrix multiplication. So when I saw the talk from the authors of the transformer paper at one of our GTC conferences, they basically said, we built the transformer in the shape of the GPU, which is very different from how physics-based methods are devised. Sort of physics-based methods are built based on the way the physics looks, and there's this mismatch between the way the physics are and what's efficient for computing. Some pieces of this are not, would be memory bound. So like this adding of numbers will be memory bound, but a lot of it is matrix multiplications, and so it would be actually fully utilizing the tensor core. And scientific computing typically is memory bound. I mean, this is, I think, maybe a bit of a straw man by poking at finite difference schemes, but there's a lot of pulling of individual numbers and adding them together in physics, and then applying exponentials and taking sines and cosines. And this sort of thing is really, it doesn't really use the tensor core at all. But if we, there are some exceptions that I think are worth noting. So spectral methods, things which are looking like matrix multiplications, I think will be interesting to see where those go in terms of utilizing the tensor core. Another interesting thing to note about ML is it's extremely tolerant of reduced precision. I mean, it's pretty nuts. So I would say the sort of workhorse precision out there is this 16-bit precision, which is the bfloat 16 that Google discovered. And this is kind of what the workhorse of transformer training is. There's even some pretty crazy examples out there of DeepSeek used FP8, which is, there's a few different variants. And then Nemotron 3, one of our LLMs, was trained off of a 4-bit precision. I mean, this is not really a lot of information in a 4-bit number. It's got like one sine, one mantissa, and 2 exponent. I mean, this is just, it's pretty nuts that this works. Numerical methods just cannot handle that. So the workhorse precision, I would say, is double. That's what most people will kind of start out with. And if you want to put 5 years of development into it, like ECMWF did, you can get down, we're starting to see models running it at single precision, and with a commensurate increase in accuracy, commensurate increase in performance. And there's some kind of fundamental reasons for this. I'm not arguing this is a fundamental limitation. It's possible that numerics could kind of catch up. There's certain things which are hard, like exact conservation. If you want to take every bit of air mass on the planet and sum it up, that's a lot of numbers that you're adding together. And so those need to have some precision to do it. And then also this fact that a lot of methods are built off of problems with relatively poor conditioning. So we can think of this as something like Clausius-Clapeyron. You have huge range of humidity within the atmosphere. So your method has to be able to tolerate, it has to be able to hold numbers which are 10 to the minus 6 and then also 10 to the 7. So not 10 to the 7, but it has to span a very large range of values. Things like large condition numbers for Poisson solves. And you can build preconditioners for each of these. I mean, like relative humidity would be a preconditioner for that specific humidity dynamic range issue. But as you kind of add these bespoke preconditioners to every problem, it can be even more difficult to maintain across your whole climate model stack. Another thing that we're seeing is so I told you about the tensor core. You might as well ask, well, why would I even bother using it? And it seems that we generally see with AI methods that the more compute you add, the better the model performs. And so you can take any number of scaling law plots out there in the literature for this. I think one nice demonstration, which is close to our domain, is this plot, which is for diffusion image transformers. And we basically see that the number, and this is during inference, so we see that the number of flops that you apply, the amount of compute you use, improves the performance across different sets of parameters, hyperparameters of the model. And so it would be great to use as many flops as possible. Whereas using the memory bandwidth is not going to improve the performance of your model. It's just sort of how do you get the data to the compute. So when we think about mapping how ML can and the accelerated computing can help with the climate modeling workflow, I wanted to go back to the slide with the cute icons. So one of the difficult aspects of high-resolution climate modeling, which I think like NextGEMS and some of these projects like this have really confronted, is how the heck do you get the data to the people who know how to make the plots? That's not necessarily easy to do. And the current workflow of this post-processing happening, all going to and from the disk, is part of what makes that difficult. On the other hand, with ML models, what you can do is you can just send the checkpoint. Send the checkpoint, and then as long as the model is affordable enough during the inference time, some of the models are more expensive, but they're all so much faster than traditional physics approaches, especially ACE. You can send them the ACE checkpoint and have them do their data analysis on the ACE checkpoint instead. And then kind of do it in the loop and save out the fields that they care about, not everything. So I think this is really one of the sort of maybe the most boring and obvious way that ML can help, but it really, just downloading, like Era 5, everybody's like talking about how do we download all the data. Well, maybe you don't need to. We have a nice package which I have found really beneficial for our research that I wanted to discuss. It's called Earth-2 Studio. It's sort of a Swiss Army knife where we take a whole slew of open models, both from our own portfolio as well as others, and it allows you to do things like combine them. So you can take an input data set from the UFS as initial conditions, run a whole forecast net ensemble off of it, and then downscale that forecast net ensemble using Cordiff. You can do this with anybody models. It doesn't have to be ours. And I found this is like a really nice kind of, here's the example. Here intern, here's an example. Please scale it. And it's been something that's really improved my research, I would say.
Does this run locally or in the cloud?
This is local. Yeah. So I'd say that we're kind of, most of our stuff is local these. Yeah. Now I want to talk about, I talked a lot about the compute. In terms of the data, I wanted to discuss some interesting aspects of that. So I guess I started with limitations, but one thing that's been shocking with this domain is just how well it seems the data-driven approach works. And I'm sure there's a lot of different hypotheses out there. Sort of the one that I've been kind of cluing in on is that chaotic dynamics really sample their own attractor well. They have this kind of fractal dimension. They're fuzzy around their own attractor. And so therefore, you don't have to worry as much about the out-of-distribution part of things. And so I think, I don't know, maybe some of the more dynamical systems experts in the room can kind of focus on this, but it seems like something like the ergodicity property is making these types of data sets a lot more densely sampled of the attractor than you would get from, say, like, shooting a cannon off and seeing if the cannonball falls, or I don't know. That was a benefit. So I think that, one slide on why I think all this stuff is working. In terms of the limitations, I think one aspect of it is just that the satellite record is so limited in duration and also quite heterogeneous within. So this is taking a plot from the Era 5 paper just for the microwave sounders. We can see we've had pretty good coverage of microwave observations of the vertical structure, but only recently did we actually start really having sounders that look at that take more like full profiles of humidity and temperature. So I think this limited length of duration is kind of showing up in a few problems. The first one is that autoregressive models do overfit, as you would expect, on long-term phenomena. So this is highlighting a figure from the original ACE paper, which shows that there's a difference in training and validation loss if you use 10 years versus 100 years of data. And it turns out that the problem is in the stratosphere. So the stratosphere is kind of slow and big and smooth. So it's easy to memorize what it looks like. And so you need at least 100 years in this case to accurately fit the stratosphere, and you can still see some overfitting there towards the end. Even worse in the ocean. So there's been some mention of the Samudra ACE paper. This is the train loss for the ocean component of the Samudra. You can see huge difference between the training and test curves here. And if you look at the power spectra of this, you can see that the physics model has a lot of long-term variability that the emulator doesn't. So it stands to reason that this ocean overfitting manifests, sees enough ENSOs, but it doesn't see enough PDOs. It doesn't see enough of that longer-term variability. Something we've seen with diffusion models, also overfitting. This is from the Climate in a Bottle paper. Here's our performance on the northern annular mode. It's sort of the first EOF of the northern hemisphere weather. And we can see that in V1 of our paper, we had the red dots. This is actually a snapshot generator, so it won't look like time series. We can see the red dots are clustering pretty closely around the observation. When we go to the test period, we can see, oh, suddenly they're not clustering as well. Well, Chris Brotherton and Ollie Wattmeyer are kind of like, hey, what's going on here? Are you overfitting? And it turns out that, yes, we were, and that if we regularize just the large-scale component of the model, we're able to sort of get the test and the training period of behaving the same. So I think diffusion models at the large scale are actually a lot more prone to overfitting than the autoregressive models are. So I'd say that that's just a kind of interesting trade-off. Another case, data simulation model. So we have our snazzy data simulation model. It's amazing what the visualization people can do. And we just sent them a buffer file and they made this plot. So it's pretty fun. And this is showing just the spectral decomposition of the error for just the temperature at 850 millibars. And again, I think maybe I'm hammering this point, train test difference. So we can see our model's actually better than a high-quality physics-based analysis up until the very coarsest modes of the atmosphere. And then we can start to see that the model is worse than physics, and throughout many scales, it's worse than the test set. So there's some strong evidence that the data simulation models are memorizing the coarsest modes of the system. To provide a bit more quantitative estimate of how much data is needed, we can go to the perfect model world. So this is from a study, I didn't put the citation here, but this is from a study that we did with a really strong intern, Scott Martin. So we generated 10,000 years of data from a climate emulator, and we treated that as ground truth and asked, well, how many years of that data do we need to make a 4-week time step? And it turns out that you need, to make a 4-week time step, which is better than climatology, this is in a diffusion model, to make a 4-week time step that's better than climatology, you need at least 1,000 years, and you see improvements up to the full duration. So yeah, if you're interested in ocean, you might need a lot of data, way more than exists in the observed record. Another interesting aspect I talked about was duration. Another aspect of data limitation is resolution. So this came up in the last talk about the CFL discussion. And so what we see with AI models is instead of being limited by a CFL, they're limited by what's predictable in the atmosphere at the given time resolution. I think it hasn't been quite understood enough that when you train a model for a 6-hour time step, it's not a 25-kilometer model. It's actually a 100-kilometer model. You can see this by looking at a twin study of the predictability at different scales in the atmosphere. And this is from one citation of this. But this curve here shows the scale at which everything higher frequency is decorrelated. So this sort of tells you what scale is predictable at a given time scale. And you can see that a 6-hour forecast requires at least, essentially blurs out to 70 kilometers. And for and one aspect of that is if you're interested in convective scale, if you follow this curve down, you need something like 10-minute resolution. And so a lot of the data sets out there for convection, like the HER, most of them are available at hourly resolution, so kind of inadequate, as opposed to ERA 5, which is quite well resolved for the timescales of interest. And so we see this especially with convective modeling. Here's one of our kind of last generation of nowcasting models, which actually just became published, kind of points out this is year-old work that's published now, so it's, things are moving fast. And we can see that for an hour time step, we basically need to use diffusion in order to get the kind of fine-scale detail that people want. On the other hand, you can do 10-minute time steps if you have a 10-minute data set available. So this is a WAF's CAS project. So if you want that detail, you need more steps. Those can either be bogus steps from diffusion, or they can be real-time steps from a high-resolution data set in time. So where am I going with this? My personal point of view is that machine learning is nice, that it sometimes is more accurate when you bring in real data. But the best thing about it is that it's fast. And it allows you to go through that development loop many more times than you would with a physics-based approach. And I think that this, why we, like, someone showed that plot of the forecast accuracy improving as a function of like the current year. And that really is just because it's a quick iteration loop. I think if you could achieve that same iteration loop with the physics-based model, you could probably get similar improvements to scale. But with ML, it's just easier to do that. I think there's a few reasons for that. The first is that where the developments in the architecture do favor dense linear algebra and ML methods, that whole arithmetic intensity. So ML is compute bound, and physics will typically be memory bound. Not to say that our two chips do have a lot of memory bandwidth, so they do make scientific computing workloads faster too. And then also, maybe more importantly, some of these data inadequacies. So the limited duration we've seen in a variety of contexts causes overfitting. The limited resolution in space and time causes blurring and not really learning the fine-scale details we care about. And so what I see here is sort of a kind of a nice combination of you could either call this hybrid modeling or training ML emulators. I think Tom gave a nice kind of overview of the two approaches, where we're using physics-based priors in some form to inform our machine learning. I sort of come down a little bit more on the ML emulator side and just using physics models to create training data because ML emulators are faster and easier to work with. But I do think the hybrid modeling approach, at least conceptually, also has some legs. So yeah, happy to take any questions we have. I know there wasn't as much interaction here. I was kind of maybe moving quickly through some of the content, but yeah, thank you.